alternative to cosmological constant by modifying general relativity in the infrared. And indeed, massive gravity is definitely not the first thing that comes into mind. And especially nowadays, modified gravity is almost synonymous with adding a scalar field. And there is some justification for adding only a single scalar field, because by the addition of a scalar, which defines a time direction, you can generalize a constant energy density to an effective fluid with an equation of state that depends on time. So it's a good way to model a dynamical dark energy-like behavior. And the framework we use for this is the scalar tensor theory class. These consist of the Horndeski terms, and then there were some new additions of beyond Horndeski and degenerate high order other terms as well. So it's a big, very big class of theories with many arbitrary functions, and depending on what you choose for these functions, you can have a different theory where you can construct a dark energy model or a different type of model which does for different purposes. And indeed, people have used this framework to develop self-accelerating models or self-tuning models or just different types of dynamical dark energy models. But things started to change a little bit after the direct observation of gravitational waves. In particular, the observation of binary neutron star merger, where the gravitational wave signal has an electromagnetic counterpart, we were able to put a bound on the speed of gravitational waves. And now we know that the gravitational waves propagate almost at the speed of light to an accuracy of 1 part in 10 to the 15, so very accurate. But there are some models which predict a tensor mode that propagates non-luminally, so something with a speed that is different than speed of light. So as a result, this observation rules out such models. So even though you're trying to modify gravity to address a problem at the very large distance scales, something that is scalar field. What this tells us for dark energy models is that the type of models that we have are simple extensions that already include lambda CDM in some limit. So if future experiments do not see any departure from lambda CDM, then we will be able to get new constraints on the parameters of these models, but we will never be able to rule them out. So they are not falsifiable. Okay. Also, the terms that remain do not really address the naturalness issues associated with the cosmological constant problem. Having said that, the scalar tensor theory framework is a very useful framework, especially for phenomenology, because most of the observables that we're interested in, that we will be able to probe in the near future, are in the scalar sector. And for example, with the weak lensing, we are able to probe the lensing potential, which is a combination of the scalar perturbations and redshift space distortions, probe the Newtonian potential, and I don't know, the galaxy distribution gives you the density perturbations as well. So most of the stuff that we are interested in is already in the scalar sector. So we have this machinery with a scalar field telling us how it interacts with the tensor field. Is it worth looking at more complex modifications of general relativity? So if I have a very complicated modified gravity theory, but as long as it has 1 degree of freedom in the scalar sector, would the scalar tensor theory be a good approximation to the scalar sector of that more complicated theory? And hopefully the answer to this will be no, so that we will be avoiding some of the conclusions reached within the scalar tensor theory class. And I will be using more massive gravity as an example to this. So by spreading the modification to the tensor sector, even though we have 1 dynamical scalar degree of freedom, we will see that actually these interactions that you get within this theory cannot be described by the scalar tensor theory class. So let me move on to massive gravity. So you already saw this in Sopan's nice talk. But let me just, for completeness, let me go over it one more time. This is the Derham-Gabadadze-Tolley action for a massive spin 2 field, which has 5 degrees of freedom. The kinetic part is just the Einstein-Hilbert term, whereas you add some potential terms that are a bit, they look a bit complicated with the square root tensors and all. But let me just go over this very quickly. So because you have a tensor field, in order to write a mass term, you need something quadratic in the tensor field. But because our field itself is the metric, its square is just a constant. So you need some reference to define the mass for this field. For this, we use a fiducial metric, which is basically Minkowski metric that is pulled back to space-time using these 4 scalar fields. And adding a mass breaks the diffeomorphism invariance that you would find in general relativity. So these scalar fields are associated with those broken symmetries. And by breaking this symmetry, you introduce new degrees of freedom, but the alternative way to represent these degrees of freedom is by adding Stickleberg fields and having a theory that is actually invariant under general coordinate transformations. So that's basically it. And our phi A they enjoy a Poincare symmetry in their field space because of the Minkowski metric in the field space. And these potentials are the DRGT potentials, and they are given simply by the elementary symmetric polynomials for unity minus square root of G inverse F, and those are defined here. And this stops at 4th order. There's nothing at 5th order. So that's basically DRGT. And what happens if you try to put a cosmology on it? First of all, you don't get any flat Friedmann-Lemaitre-Robertson-Walker metric. The problem is you find that the equation of motion for the scalar degrees of freedom, the Stickleberg fields, force you to have no expansion in that case. So you don't get a cosmology. But what we figured out was actually if you have curvature, you can have a cosmology. This would be an open universe solution. This is because the Minkowski metric of the field space can be put into a form that looks like an open universe. So it's the open chart of Minkowski. And this is achieved by having a field configuration that is given in this way. And K here is the spatial curvature that is negative. But once you use this setup, you find that the F mu, the fiducial metric, is simply has this open universe form, but this is actually just Minkowski because you can see the TT component and the spatial component are related. And this is the thing that ensures that this is a Minkowski metric. And for the physical metric, we also choose the open universe ansatz. And this is because we want to have the same symmetries in the 2 metrics in the same coordinate system, such that the perturbations do not get some broken statistical isotropy, for instance. So with this setup, we can derive the background equations of motion. Let me first define a few things. Here, this psi, given here, is basically the ratio of the 2 scale factors in the 2 metrics. If you compare these, this is nothing but the ratio of the scale factors. And C tilde is basically defining the light cone on the F metric. It's kind of like the speed of light for the F metric. And with these, you can construct these functions L and J, which contribute to the background equations. Both L and J are just polynomials of this psi. And in DRGT, these alpha parameters are just constants. So it's just a polynomial of psi. And you can see that the contribution from the mass term is from L function to the Friedmann equation, and there's a contribution to the H dot equation as well. I've also included some matter, just a single fluid with conservation equation like this. And finally, the thing that's new is the equation of motion for the Stickleberg fields. And this is a constraint, actually, and it has 2 possible solutions. One solution is this parentheses being 0. But if you do that, you will find that the physical metric just turns into Minkowski metric in open chart. So this is not a cosmological solution. Therefore, in order to get a cosmology, we have to have J equals 0 solution. if j equals 0, j itself is just a polynomial of psi. This will give us a solution for psi that is constant. Therefore, L will be constant, and the contribution from the mass term to the Friedmann equation will just be a constant. So the background will be exactly like lambda CDM in this case, in DRGT massive gravity. The problem, however, arises at the perturbation level, and we find that the similarity with lambda CDM also extends to the perturbation level in an unwanted way. When you look at you have now, this is a 5 degree of freedom theory. So in addition to the 2 tensor modes, you have 1 scalar and 2 vector polarizations of gravitational graviton. And when you look at the scalar and vector modes, their kinetic terms turn out to be proportional to this j, whereas j was already forced to be 0 at any time. That is a problem, of course. And this indicates there's a strong coupling issue. It's an infinitely strongly coupled system, which is telling you that this whole background does not obey the perturbative approximation. You cannot do perturbation theory within this this background, and basically you immediately go out of the reach of the effective field theory at 0 energy, basically. And that's basically it. These are the issues associated with the usual DRGT. And as Sopan nicely summarized in his talk, people started looking for extensions. And this is how I see the potential resolutions. One option is to break the symmetry of the background. So instead of insisting on an exact Friedmann-Lemaitre-Robertson-Walker, you might look for some solutions that are homogeneous and isotropic only approximately. One option is was provided in the early days of DRGT massive gravity. This is there are some inhomogeneities, but within the observable patch, the universe averages to a homogeneous and isotropic universe. In that case, you can actually avoid some of these problems, or you can break isotropy in a way that your physical metric is still isotropic, but there's a disharmony between your 2 metrics, so that they're not isotropic in the same coordinate system, although they can be isotropic in their own coordinate system. And these types of approaches can also address this. Or you can have a universe where you have spherical symmetry. And some of these work better than the others, but at the end of the day, once you start breaking symmetries, you will encounter some technical problems. Most of our observations rely on a working perturbation theory, and doing perturbation theory on these in a precise way is quite difficult in these types of models. Another option is to add more degrees of freedom. You can add a scalar field, and there are some ways to do this. You can also allow the fiducial metric that was non-dynamical in the case of massive gravity to have its own dynamics. So it has its own Einstein-Hilbert action, and so on. Then you don't have to kind of artificially set the Stickleberg configuration, and instead let the F metric reach whatever value it has in a dynamical way, starting from some initial conditions, of course. Or you can add more tensors, and there are lots of things that I'm missing here. I apologize if I didn't include your favorite model here, but there's no limit once you start adding degrees of freedom. But I think the most natural ones are either letting the F metric to be dynamical or adding one scalar field that controls the mass in some way. And finally, you can also break the symmetry of the theory. So in the first option, it was the symmetry of the background while keeping the theory the same. In this one, you're breaking the symmetry of the theory. And there's a good work, a lot of activity in this section as well, mainly on theories with invariance under rotations. So these types of theories, both of these actually, break the time reparametrization symmetry. So they have a preferred time direction, and they eventually break Lorentz invariance. And so SO3 invariant theories just have the rotational invariance, whereas theories like minimal massive gravity, they have a very well engineered actions such that you don't need a scalar or a vector graviton degree of freedom. So these have only two gravitational waves, the tensor modes, that have massive dispersion relations. But both of these break Lorentz invariance. So what will I do now? What I will do, I will take the third approach, but instead of breaking Lorentz invariance, I will keep it. But I will break something that doesn't seem to be too essential, maybe, at least for the types of applications I'm going to talk about. I'm going to break the translation invariance, and this will allow me to keep 5 degrees of freedom. So this is explicitly what I'm doing. So the translation invariance that I'm breaking is the global symmetry in the field space. If you remember, the scalar fields, the 4 Stickleberg fields that were associated with the broken symmetries, those lived in a space that was a Minkowski space. The field space metric was Minkowski. And because of the Poincare symmetry in the field space, I was only allowed to write the derivatives of these scalar fields. But if you break the global translation invariance, that will allow you to use the field itself in the action. And this theory space is actually continuously connected to DRGT. So DRGT lives in a corner of this theory space. And there's no degrees of freedom that is introduced in addition to DRGT. You have 5 degrees of freedom, and you preserve Lorentz invariance. You have you only break the translation in the Poincare invariance. So, but what this the advantage of doing this is that now we get a new invariant, which is the norm of the phi, in a way, and we can use this new invariant as a building block. This is the X that I'm going to use. So the way to find the complete class of theories is then there are 2 ways. Either you can choose the way of doing it in a brute force way, or maybe more honest way, is to determine all the possible invariants you can write in your action and write them down, and then require that you only have 5 propagating degrees of freedom. So normally, when you add arbitrary terms in massive gravity, you might end up with a dangerous 6th degree of freedom. This is the one that is associated with the Boulware-Desert instability. So in order to avoid the Boulware-Desert ghost, you have to go through all of your terms and find the conditions under which they only give you 5 degrees of freedom. We found also a shortcut. You can just start from DRGT and then choose some convenient metric variables by, for example, you can now, with the addition of this new invariant, you can do conformal transformations on your metric, and also you can deform your internal metric via some disformal terms as well. Once you do that, you can actually generate all of the terms that you would get from the first approach. But whatever approach you choose, what you end up with is this new class of massive gravity theories. And so this has 6 arbitrary functions of the new invariant. So you get some non-minimal coupling to curvature and some counter terms, of course, for fixing these. And you get all the DRGT mass parameters being promoted to functions of X. And finally, this fiducial metric gets deformed by this formal term defined by this new D function. So this is basically a very general class of shift symmetry broken massive gravity theories. Let me give a few examples. Of course, this is a class of theories. By fixing what the functions are, you will be defining what your theory is. And DRGT can be obtained when you set the non-minimal coupling, when you turn off the non-minimal coupling and the deformation in the field space metric. And if you let all the mass functions to be just constants, you end up with DRGT. And the next to minimal example would be the generalized massive gravity, which was actually discovered a few years earlier than us, and which was actually the motivation for looking for this general theories. And in the case of generalized massive gravity, Again, they don't have any non-minimal coupling or deformation, but these functions are there. So this is basically DRGT with the coupling constants being promoted to functions. And throughout my talk, I will step by step simplify the picture. And this is the first simplification I'm doing because when I work with the most general thing, it's really difficult to say precise things. So I will be choosing the generalized massive gravity for simplicity for this discussion. So this is the action that I'm going to use. And as I said, this is just DRGT, except now alphas are now functions of phi A, or X. And in this case, we look for a Friedmann-Lemaitre-Robertson-Walker metric, and I'm going to basically build cosmology now. Now, the conditions for homogeneity in isotropy basically can be summarized in two conditions. One of them is that F mu should have the same Friedmann-Lemaitre-Robertson-Walker form as G mu should have the same symmetries in the same coordinate system. This is already something we've done. We've imposed in DRGT. But now, in addition to DRGT condition, we also have this explicit dependence on the field itself in the action here. So we have to also make sure that this is not breaking homogeneity. So this should be only a function of time. And it turns out there's only one way to do this, and this is by choosing the Stickleberg fields in exactly the same way that I showed you before. Only the open universe is allowed in this case. And when you look at the new invariant X, or phi A, you find that this is just a function of time, where f of t was the way we parameterize the time-dependent part of these Stickleberg fields. And with this, our fiducial metric can just be written as Minkowski metric in open chart. That means we're going to look for open universe solutions. And let me write down the background equations of motion for this theory, or for this type of setup. First of all, the way we define psi and c tilde is exactly the same as in DRGT. The only difference is now alphas are functions of the new invariant, or time, in this case, at the background level. And you see that the Friedmann equation is exactly the same, h dot is exactly the same, and we have some matter. So the difference arises on the last equation, the equation of motion for the Stickleberg field. If you remember, in DRGT, J was 0. But now, because of the variation of these mass functions, we are now allowed to have a J that is non-zero. And this is the thing that actually fixes all the pathologies of DRGT cosmology. And namely, the issue had to do with perturbations. I'm not going to go into the detail of perturbations, but let me just summarize it in a nice picture. Again, I'm doing another simplification. It's really difficult to show all the parameter space. So I'm going to set two of these mass functions to be 0. I'm just turning them off. And I'm setting two of the functions to be constant only. So the only departure from DRGT is included in this alpha 2 function. And you can see the new invariant comes only linearly. So this is my choice. So this is my theory. And for this theory, this Q parameter is the thing that really measures how far away from DRGT you are. And depending on the sign of Q, you can get a completely different stability behavior. So for Q positive, it's on the left, and Q negative is on the right. And I'm showing the parameter space, so alpha 3, alpha 4 space. And the green regions in left and right correspond to the points where all of the stability conditions from perturbations are satisfied. So on the green region, your theory, your cosmological model is stable against perturbations. But the light blue region where you break at least one of those stability conditions. The white region is where you don't have any solutions because of the square roots. So this is all interesting, okay, but the problem is outside of this dashed region, cosmological constant that you get from the massive gravity is actually negative. Only within the dashed region you have a positive cosmological constant. So where we want to be, if we want massive gravity to explain all of the cosmological constant, all of the late time accelerated expansion. Where we want to be is to be in the intersection region, overlap region between this dashed area and the green region, which I marked in yellow here. So for positive Q, this is a finite region. For negative Q, it extends to infinity. So that's basically it. It is possible, depending on your parameters, to have a stable cosmology in this very simple setup. So what I'm going to do, I'm going to do further simplifications. I don't want to carry around a lot of parameters. I'm going to fix my alphas. And the way I do it, I'm fixing one of them to be 0 again. So I'm choosing Q positive and alpha 3 to be 0. And I'm just choosing this point where alpha 4 is 0.8. And from now on, all of the things that I'm going to talk about are going to correspond to this single point here in this single theory. So what does the background look like then? So what is the mass term doing in this setup? I'm adding some dark matter, like 30% pressureless matter, and I need some cosmology for consistency of my numerical solutions. The value of m, we fix it by requiring that the Hubble rate today corresponds to h naught. That will give you typically a mass that is of order of Hubble today. So what you end up with is, here I'm showing the equation of state, the effective equation of state coming from the mass term as a function of the redshift. And here, as Q decreases, the effect of this term gets smaller. That means you're getting closer to DRGT. So as I'm moving up here, you can see that I'm approaching W equals -1, where if you remember that DRGT cosmology is exactly the same as lambda CDM at the background level. So you're basically getting a cosmological constant as you decrease this value of Q. You can also see that this equation of state is actually bouncing, and Q1 is actually a marginal example where this bounce happens within today in our past. And what will eventually happen is that the theory or the model will go so far away from DRGT is that it will start turning back. And at one point, it will cross W equals -1. And then you will end up becoming unstable again. So there's a future instability in these types of models, at least for this theory, which I don't really worry about because this is an artifact of the very quick time dependence that I introduced in this alpha 2 function. In principle, you have a lot of freedom to control these types of effects. So, and in addition to that, it's happening in the future. I don't worry about going outside of effective field theory right now. So that's what I really worry about. When you look at the departure in the expansion rate from lambda CDM, you see that there's a 1% departure from lambda CDM, and you have a slower expansion rate with respect to lambda CDM. And as you go closer to the RGT, you can see that this departure becomes smaller and smaller. So this is what the background does. But also, of course, we have a scalar graviton, and it contributes to gravitational interactions. And as a result, it will change the strength of gravity. We can look at the perturbations, and we can find the equivalent of the Poisson's equation. Here I've absorbed all the effect from the scalar graviton into the definition of an effective gravitational constant, which is no longer constant, of course. And here in this plot, I'm showing the departure of this G effective from the Newton's constant. And it is typically of order 10% level. And again, as you approach to DRGT, or lambda CDM in this case, you see that the departure from G Newton becomes smaller and smaller, and your effective gravitational interactions becomes closer to strength of gravity becomes closer to the standard GR1. Okay, and since we have a modified expansion rate and a modified gravitational strength, both of these effects will affect how the density of perturbations, matter density, evolves with time, of course. So if we look at the density contrast for matter sector normalized to its GR value, you see that the matter will grow faster with respect to GR, or grow more with respect to GR. And this departure is about 1% level. That is actually within reach of new missions like Euclid. Okay, so this is up to here. If you're familiar with these types of models in scalar tensor theory, you might think, okay, this is not very different than a typical dynamical dark energy model. Maybe the profiles are a bit different. It can be unique, but I can always go ahead and try to backwards engineer a scalar tensor model, which gives a similar signature. The difference now arises in the gravitational wave sector. So up to here, if I don't see any departure from lambda CDM, I can always choose my Q value smaller and smaller to get closer to lambda CDM and be in agreement with data. But what happens in the tensor sector, our gravitational waves have masses. They are non-zero masses. And here, as you decrease the effect of Q, so you approach to lambda CDM in the scalar sector and background, what happens in the tensor sector is you're increasing the mass. Okay? So even if we don't see any departure from lambda CDM, although the constraints will become tighter for our parameters, what will happen is it will predict a larger and larger mass for the graviton. So far we're fine. So the tensor modes see the usual light cone. So if you look at the dispersion relation, the coefficient of the momentum is 1, because we have used as the kinetic term the Einstein-Hilbert term. But we still get a slight modification to the speed of gravitational waves from the tensor mass. And for this order, like order 10 Hubble rate mass, this is like 10 to the minus 32 electron volts, and this is well within the bounds of LIGO. Okay, so, and as the last topic, since we have a different strength of gravity which affects the structure formation, then you might worry about this changing, spoiling the solar system tests, for example. This is the topic that David very nicely explained about screening. And I will show you now that we have naturally embedded Weinstein screening, as it is very typical for massive gravity theories. But it is always good to check that it works. And this is what I'm going to do. I'm going to add some nonlinear scalar perturbations around Friedmann, Lemaitre, Robertson, Walker. And I'm going to use a Newtonian gauge for this so that it is diagonal, so I can easily take the square root of the tensors as I do in massive gravity. And remember that I'm not using a perturbative expansion here. So these are like, this is an exact difference from the background one. I will do some simplifications later, but for the moment, these are exact. This is not a perturbative expansion. And there are some similarities with the scalar tensor theories. We find that the perturbations to the spatial Stickleberg fields, that is our scalar, are actually this pi, is analogous to the scalar in scalar tensor theory. So there are lots of similarities in the equations when you do a comparison. But there is a difference. In massive gravity, you also have the time Stickleberg field. And because of the form of the DRGT potential, that one is non-dynamical. And this is the thing that brings the differences from the usual scalar tensor picture. It's more like a constraint system with the addition of this auxiliary field, so to speak. So what I'm going to do, I'm going to consider spherically symmetric sources like this, and I'm going to use the short scale regime. So this is kind of like the quasi-static approximation, but extended to a non-perturbative way. So r is going to be, the radial distance is going to be of order epsilon. This is the small distance that I'm choosing. And to be consistent in the Poisson's equation, and in addition keeping relevant nonlinear terms, what we need is to, I'm going to keep the density perturbations order 1, and all the other perturbations I'm going to assume they're of order epsilon square. What this does, in Poisson's equation, you're relating the second derivatives of the metric perturbations to the density perturbations. So because we're in the short distance limit, each spatial derivative brings me a 1 over epsilon. So this will allow me to have a consistently a Poisson's equation or an equivalent of that at leading order. So this is the approximation I'm doing. And as a result, as long as I have enough derivatives, I will be able to express any term in the perturbative expansion. And when you look at the gravitational potentials, you can solve the Einstein's equations exactly within this, at leading order in this expansion, of course. You can solve the the gravitational potentials. And in GR, of course, these two are the same, but we're not in GR anymore. We have this modified gravity effect coming from this pi term, and there's a difference that arises in between the two. And here, delta m is the total matter perturbation. Basically, it's just the integral of delta rho over the volume. Okay, so at the level of Einstein's equations, these are very similar to Horndeski ones, the ones that you would get from Horndeski. But when you look at the Stickleberg sector, things are very different indeed. This is because we have a non-dynamical field. We can solve its equation of motion and replace it back in the Stickleberg equation, and you end up with things that are interactions that are never truncated, at untruncated nonlinear interactions. Whereas in Horndeski and those type theories, usually the self-interactions, even in a non-perturbative approach, they stop at some order. But because we have 1 over some interactions that appear in the denominator, this is the basically giving us an infinite series of interactions if you choose a perturbative picture. So once you reduce the equation for Stickleberg fields using the solution for the temporal one, you end up with this master equation for the pi prime. The prime is the spatial derivative. I didn't replace the solutions for the gravitational potentials, but once you do that, you see it's just a 9th order polynomial for this pi prime. And there are 9 solutions, of course, but the thing that will guide us in choosing the right solution for this is the linear solution. In the linear regime, you have a unique solution, which goes like 1 over r squared for pi prime. So we then solve this equation numerically, and we find there are several solutions, of course, but only one of them matches the right linear behavior. And this is, again, a place where things are very different than a scalar tensor theory. In scalar tensor theory, the types of solutions you would get to the equivalent of the master equation would be either constant or increasing with time, with space. But here we have a denominator which presents a new type of solution. So we find some sets of solutions that are adjacent to the roots of this denominator. Here in the dashed red line, I'm showing the solution to this denominator, one of them at least. And 2 of the solutions, the full equation solutions, are adjacent to it. And if you zoom in, it never crosses. You can always show that it never crosses. And we have done some analytic estimates, which is shown in this dot dash line, and it really matches the numerical solution perfectly. And only the solution that's shown in brown actually connects to the right linear or perturbative behavior. So we then choose this one. as our solution. And as you see, this grows like R. So as you go to shorter and shorter scales, pi prime actually goes to 0. And with this, we can define the transition radius from the linear regime to the nonlinear regime as the Weinstein radius, because we have this is associated with the Weinstein screening mechanism. And the transition radius is given by this. This is also very typical for Galilean-like theories, but the way we reach it is completely different than any scalar tensor theory. And let me also be a bit more specific for Sun. Adding the Sun, the Weinstein radius is at 100 parsecs. We can look at the evolution of the, well, not evolution, but the radial dependence of the post-Newtonian parameter today, evaluated today. And our analytic estimates tells us that 1 minus gamma goes like R cubed. So as you go to shorter and shorter scales, you end up with effectively GR. And the Cassini, the bound for 1 minus gamma is already satisfied at 0.1 parsec, which is well beyond the size of the solar system. So this is basically showing the same things that I've told you about in a plot. Here, the blue line is the phi potential with respect to GR, and the orange one is the psi1. And psi1 also in the linear regime at large distances, it is modified with respect to GR, but you have to zoom in to see it. It's quite small. But nevertheless, it's modified. And their ratio is giving us the post-Newtonian parameter. And you can see that it's different than the GR value at about a few percent level in the linear regime, where which is relevant for our accelerated expansion. But once you get closer to the origin, this is again the Weinstein radius is shown in the vertical line. It quickly goes back to the GR value, and it is already within the bounds at 0.1%. Sorry, parsec, not percent. So basically, that's it. I talked about a new class of Lorentz-Riemann theories, which have 5 degrees of freedom and that extend the DRGT massive gravity in a smooth way. And I basically defined a theory and gave you a model, which is a proof of principle model. To be honest, that's basically the first set of parameters that we chose, which usually never happens. But the first thing we tried seemed to work. So which probably suggests to me that it's likely that there are many, many other models that you can construct in this theory. I don't think it would be possible to have randomly selected the only working model from this giant mess. But this model is perturbatively stable. It gives you a dynamical dark energy with a phantom-like equation of state. It has a modified matter growth that can be probed, but it has also massive tensor modes. So far, they are currently within the LIGO bound. It has a successful screening mechanism, and it can be distinguished from lambda CDM and other scalar tensor models with the signatures that render this potentially falsifiable. Something I didn't address is the smallness of the cosmological constant in massive gravity theories is so-called technically natural. This is because the effective cosmological constant is determined by the mass of the graviton, and this mass, its smallness, is protected against quantum corrections. This is because of the symmetry you achieve when you send mass to 0. You have GR with the diffeomorphism symmetries, so the corrections to the mass come proportional to the mass itself. So as long as it's small, it will stay small. There's some ongoing work. We want to make sure that we can avoid all of the conclusions that are reached in the scalar tensor theories. This includes gravitational wave instabilities. So this is something we're looking at right now. And so far, we only focused on a small corner of the theory class. We have scratched the surface, so to speak. But there are lots of things that we haven't looked at. We have only done one application of this. But the main message of this talk is that the scalar sector of massive gravity theory is not fully described by the scalar tensor theory. So if you're going to draw some conclusion based on scalar tensor theory, you have to be careful. You have to check precisely that this is the case. So I think this is where I stop, so I can get some questions as well.
Thank you very much. Thanks for this excellent speech. I think you said everything and there is no question to ask. However, if anyone has a question, they can ask it.
Thank you.
In addition, if you are agree, the next speech will be held at Google meeting here. And
in by gravity, so as a result, you have 5 gravitational degrees of freedom. This is basically the Poincare representations of a massive spin 2 field, right? It's 2 spin time plus 1. But if you add another Einstein-Hilbert term for the F metric this time, then it becomes dynamical, and you add 2 more degrees of freedom. But now there's no relation to Stickleberg fields anymore. F itself will be a dynamical field, and you will have to solve its own equations of motion as well. So that's the difference, basically. In bigravity, your second metric is no longer just a reference, but it is a dynamical field that introduces 2 more degrees of freedom. And if you look at stuff like flat space-time solutions in bigravity, you see that there's 1 massive graviton and 1 massless graviton, so to speak. So the 7 degrees of freedom are kind of distributed in that way. Does it make sense?
yeah, I see. Thank you. Thank you for your nice explanation.
Oh, I noticed I couldn't share my screen. I was explaining over the action, but yeah, I just realized that it was giving me a warning that I couldn't share, but sorry.
Nice. Don't worry. Any question? Okay. Okay, it's good. Thanks again to Dr. Emir Gümrükçüoğlu. And then